My name is Arvind. I'm coming from Monash University, Malaysia. I'm doing my PhD, currently in my final year. I'm here to share my experience of using Mathematica and Web Mathematica in my research in engineering. Right? Uh, I did my degree in Monash as well, in the same institution, and I graduated in 2014. Um, I was taught to code in MATLAB, and as well as C++. I will share with you why I moved to using Mathematica instead of using other softwares. All right. So before I go there, let me introduce some background on my research. All right. Okay. So in engineering, um, uh, it has been increasingly complex in modern engineering. But however, engineers are constantly striving towards finding products that uses the least amount of resources. But to find the a very high quality product, there are some analysis that you have to do on the product, such as reliability analysis and robustness analysis. All right. Um, and this is done from micro scale design, such as micro electromechanical chips over here, up to mega scale structures, such as the bridge that you see, even the cars, like your crash test design and things like that. Okay, so this robustness and reliability analysis mainly depends on the distribution of of a quantity of interest. For example, let's say, let's say I drop this phone from this point. All right. So what happens is when the phone drops, it deforms in some manner. All right. So when it deforms, what I would like to know is how much is the deformation, and what is the variation in the deformation. So based on this knowledge, I will be able to do some reliability test and robustness test. Okay, so from a mathematical standpoint, knowing or calculating the distribution of this quantity of interest is very complex. Or put it in this way, it is almost an impossible task. But then the reverse, but 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 the reverse is actually much feasible, whereby you find the properties of your distribution, such as the mean, such as the standard deviation over here. This is the mean. So the mean will actually give you the expected value of whatever the quantity that you are looking for, and and, and the other quantity is your standard deviation, which will give you how wide or how narrow is your distribution. All right. There are also other quantities such as skewness. Skewness will tell you how asymmetrical, and also there's kurtosis, what is the peak, how far is the tail, and things like that. So I will not go into that today. So the research at Monash, or what I am doing, mostly is on finding these parameters of the distribution of this quantity of interest. And using this, we will actually model this distribution, and from there we can actually find do the studies on reliability and robustness. So just I'll introduce some mathematical notations. Let's say this quantity that we are interested in is denoted using y. All right, and it is represented using some function of input variables, okay, with x, and usually the x is known. The distribution of x is known. For example, if I drop my phone from this height, okay, the deformation on my phone is going to depend on my this height and things like that. All right, the material of my phone. So these inputs are usually known, but from this input, our interest is to find the distribution of y. Right? So one of the objectives of my research is to find an analytical approach, a symbolic approach, all right? Because currently in engineering, it is very complex to perform this task. So most of the methods are usually numerical, okay? So, yeah. Um, right. This is the outline of my framework. Let me increase this. Okay, that's the maximum. All right, this is the outline of my framework where there's an input and then there is some algorithm in between, and the output is actually your distribution parameters, such as your mean or standard deviation and things like that. So what you see here down here is your algorithm, is my algorithm actually. Okay, let's say, all right, this one. Okay, this is the expression. In this case, it is x1 squared plus x2 squared, right? So when I run this, this will actually give me the standard deviation of the quantity that I am looking for in terms of the mean, the M1 of x1, and also standard deviation and mean of x2 and x1. Right. So so this gives me the standard deviation. Similarly, we can also find the mean and as well as the skewness and the kurtosis, and we can actually find how the distribution looks like. So one of the selling point that I moved from MATLAB, using MATLAB to Mathematica for my research, is that Web Mathematica. After this discovery, I wanted to share my discovery with other researchers all over the world. So the only thing that I could find, the tool that I could find to share this is Web Mathematica. All right. So let me show you. This is actually powered by Web Mathematica. All it took me was 1 week to actually create this web page, because Web Mathematica gives you this documentation, step-by-step procedure for you to set up this web page and create a GUI. But this of course takes some learning of Java and HTML. Right, but using that, it forms an interface, a connection with the Mathematica kernel, whereby you can actually run the code. For example, if I click this, if I click that, it will actually give me the same expression that you saw earlier in the codes. Right, so this was a huge milestone for my project, and using this was sort of a springboard for my project, whereby it was applied in real engineering models. For example, this is just a case study. This car. So the objective here is to minimize the weight of the car, subject to some reliability. They have 11 constraints, such as the colored segments that you see in the car. So due to some safety regulations, all right, and this distribution of this, the reliability analysis is made from this distribution found using the software that I created from Mathematica. And as you can see here, the reliability is 90%, right? So so the result is that all the constraints should meet that 90%. Since this is an analytical approach, the results are quite accurate. So none of the constraints actually goes below that 90% constraint. And most importantly, when we compare against the other methods, such as the numerical approach, since it is an analytical approach, the speed is actually about 5 times faster. So this is the main advantage of these findings, and using that we have also published a lot of journals and formed some attachments with universities from other countries, and yeah, also I would like to use this opportunity to thank OEMs Intipaka, because when I was doing my final year project, that is when I started this project. And back then, there were no Mathematica subscription in my campus. So when we requested OEMs Antipaka, they helped us out with licensing and stuff. And then only after 2 years, we obtained our license campus-wide. So that is why I would like to thank, and I'll wrap up my presentation here. Thank you.